You either get it or you don't.
In Chapter 14, we'll be looking at ethers and epoxides, and also thiols and sulfides. In the picture that you see here, there's cigarettes with wafts coming out of it, and different molecules coming out of the smoke. Cigarette smoke contains many compounds that have been shown to cause cancer, and in this chapter we're going to look at these reactions will involve formation and reaction of epoxides, which we've seen a little bit of in the past. Epoxides are a special category of ethers, and these compounds will make up the main part of this chapter. We're also going to look at reactions of ethers, epoxides, and related compounds in the sulfur category. So an ether, if you recall, includes an oxygen atom that is bonded to two R groups. R groups can be alkyl, aryl, or vinyl groups, and they don't have to be the same on both sides. And if you look at the compound below, would this be considered an ether? Hopefully you are saying no. This one is an ester because of this carbonyl here. Here are a couple of examples of different ethers, including vitamin E, which is an antioxidant, and there's the ether compound. Morphine, which is an analgesic opiate that is highly addictive. This is used to treat severe pain. And fluoxetine is a powerful antidepressant, which is also sold under the trade name Prozac, and that has the ether group there. Ethers cannot hydrogen bond to other ethers because there's not an OH present, but it can hydrogen bond to alcohols or water. Most ethers have low boiling points, again because they don't have that ability to hydrogen bond. So their primary intermolecular forces are the van der Waals forces. So their boiling points are similar to the alkanes of similar molecular mass. Ethanol has a high boiling point of 78 degrees due to the OH hydrogen bonding. Dimethyl ether is around -25. Propane is -42 degrees. These are similar in mass, but this slight bit of dipole here increases the boiling point slightly. Small ethers are soluble in water, using that 4 carbon per oxygen rule. Diethyl ether is usually made in the industry by acid catalyzed dehydration of ethanol. So what happens is ethanol gets added to acid. The oxygen lone pair can grab a hydrogen. That has a positive charge. Another molecule of ether can do an SN2 attack here because water is a good leaving group. And we get a proton transfer in the last step. This gives us diethyl ether. The Williamson ether synthesis is a way that many ethers can be made, especially asymmetric ethers. The first step is one we've seen in chapter 13, where the sodium hydride can remove a proton from the alcohol, and that's where we form the alkoxide. And when you have that present, this alkoxide, this is a good nucleophile. We add to it an electrophile. Then we can do a nucleophilic attack and add the 2 carbons to form the ether. So this is the Williamson ether synthesis. So the first step is a proton transfer. We get a nucleophilic attack followed by a loss of leaving group, and that forms the ether here. So if we're doing this reaction here, sodium hydride will remove this hydrogen to form the alkoxide. The alkoxide will attack methyl iodide, CH3. If we wanted to make the same compound, this is methyl tert butyl ether. Or MTBE, which is a common solvent. We can make this MTBE using the method on top, but it does not work as well when you start with methanol plus sodium hydride and the tert butyl iodide. The reason that this does not work very well, if you think about this step in the mechanism, the O- is attacking here. It's doing an SN2. If we're doing an SN2 here, that would be on a tertiary carbon, so that's why that one does not work. and that is due to sterics. We can also make ethers using the mercuric acetate reaction. If you recall, we reacted the alkene with water here to get us the alcohol at the Markovnikov position. If we do the same reaction but instead use an alcohol, that will give us the ether, again at the Markovnikov position. So if we want to look at designing a synthesis for the following ether, you can think about which ways you can break them apart or which methods you want to use. One of the methods which we just saw in the last slide was using mercuric acetate. So if you were going to do that, you can think about this being the alcohol part of the equation. So if I used alkene, cyclohexene, and the alcohol would be just ethanol, followed by sodium borohydride. Alternatively, you could use this part as the alkene, and cyclohexanol as the alcohol. So that's two ways you can do it with an alkene. You can also use the Williamson ether synthesis, which starts with an alcohol. So we could think of cyclohexanol here. We would need NaH to remove this to form the alkoxide, and then we're adding 2 carbons, so that would just be ethyl bromide. And we can use this part of the molecule as the alcohol. Sodium hydride will make the alkoxide. We have the bromocyclohexane. This will get you the product. This one will be slower than this one here, just because we're doing an attack at a secondary carbon, which SN2 can do, but it will be slower versus the primary carbon. Once you form an ether, it can do a couple of reactions. One of them involves a reaction with acid, and initially we'll get a proton transfer. Plus X minus. This is now a leaving group. Here we have ethanol as a leaving group, which makes this partially positive with our leaving group, also known as an electrophile. So this can attack here and break that bond. So you form CH3 to the X plus O, CH3H. So we get methanol and the alkyl halide. So if we add an ether to the halogen, one of those parts of the ether gets the halogen, the other half becomes the alcohol. And then with that alcohol that was still there, with the same proton transfer, so now water is our leaving group. We've got an electrophile here. Another alkyl halide plus water. So for this problem, we can draw a complete mechanism and predict the products following the acid-promoted cleavage. The first thing that we're going to do is do a proton transfer. Plus X minus. We want to look for our leaving group here. This is a very good leaving group. We want to look to see where we can do our SN2 attacks. The SN2 can only happen at the R and not at this position. We can't do an SN2 on a benzene ring. And we get the halogen there. So HI and HBr are good halogens to use for this cleavage reaction. HCl is less effective and HF does not work. Predict products for the reaction below, draw a complete mechanism. Those are the products that you would see there. So oxygen undergoes a proton transfer with HBr. Br minus is kicked off. This is now protonated, which makes it a good leaving group. Br minus will attack the electrophile, kick off the leaving group. We get alcohol plus ethyl bromide or bromoethane. The alcohol is going to do a proton transfer, kick off the Br. We now have water as our leaving group. Br minus can attack this group here, kick off the water, and we get bromocyclohexane. For cyclic ethers, the size of the ring determines the parent name of the molecule. You do not need to memorize all of the names for these ones. The ones that we're going to be looking at are epoxides, which are also known as oxirane. So if you can remember epoxide, you should be okay for the nomenclature part of naming cyclic ethers. This is also called oxirane. If it's a 4-membered ring, it's an oxetane. 5-membered ring is oxolane, and a 6-membered ring is oxane. Again, you only need to know epoxide. We can have substituted oxirane or epoxides. Ethylene oxide is the simplest one that has just hydrogens around the ring. Disparler is a sex pheromone from the gypsy moth, which contains an epoxide, and this other sex pheromone of the female American cockroach is periplenone B, has 2 epoxides. An epoxide can have up to 4 R groups, and although they're pretty unstable, they are found in nature, as you have seen. In order to make an epoxide, there's one of these reactions we've actually already seen in chapter 9, when you reacted an alkene with a peroxy acid, remember seeing as RCO3H. You would get an epoxide that usually was followed up by water to make the diol. But if you just have RCO3H, this gives you the epoxide. In this semester, we're going to have to get a little bit more specific than RCO3H. So you have to pick an R group to use as your peroxy acid to make an epoxide. One of them here is peroxyacetic acid. The other is metachloroperoxybenzoic acid, or MCPBA is the abbreviation most commonly used. So if you have a cis alkene, you react it with MCPBA, which is the equivalent of RCO3H. We get our epoxide. The hydrogens are going to be cis to each other, and the R's will be cis to each other as well. So you get a cis epoxide. If you start with a trans alkene, you'll get your epoxide. Your R groups will be trans to each other, and you'll get a trans epoxide. Epoxides can be formed using halohydrons. If you remember from previous chapters, you can make a halohydron using a Br2 and water from an alkene. Now if you had this halohydron, you can add a base such as sodium hydroxide, which will grab a proton. So we have a proton transfer. With a minus charge there. And now what can happen, because this is on the back side of the Br, we can do an SN2 attack here on this electrophile with a good leaving group. So leaving group, electrophile. This is an SN2 reaction that's intramolecular, so it's within the same molecule. And because it attacked from the same face as the oxygen, that's epoxide that you will get. So for this one, must have anti-halohydron. So if I have a cis alkene with MCPBA, I'm going to get a cis epoxide. If I use Br2 and water to get the halohydron and then add sodium hydroxide to that, I will also get the cis epoxide. The thing that will be very useful in synthesis is using ring opening epoxide reactions. Because of that significant ring strain, there's going to be 60-degree angles in there, so they're very reactive. We can use them a lot in synthesis to add 2 carbons and an oxygen. So if we look at some reagents that might react with epoxides, we can look at some reagents that might react with an epoxide to provide a specific functional group. So if we had an epoxide, there's a lot of angle strain here. There's 60-degree angles. We add OH minus. This is partial negative, partial positive, partial positive. Even though this is partially positive, this is a very good electrophile. We have a built-in leaving group, and the added ring strain is going to make it that much more reactive. So a OH minus or some other nucleophile can do an SN to attack here. The electrons go onto there. And I've added an OH. This becomes O minus. Water's just in solution. We can get a proton transfer. So this is a way to form a diol. There's lots of different nucleophiles that we can use, as you can see here, to open up epoxides. If you have an RONA, or this oxygen minus, that can open the ring up from one side to give you OR. So if you need an ether plus an alcohol, with NaCN, the CN is the minus part. So you'll get the alcohol and the CN. With sodium thiol, we get the OH, SH. We can use the Grignard to form a new carbon bond. Lithium aluminum hydride is the source of H minus. That will add an H. So anytime you need to add 2 carbons and an oxygen, an epoxide is a good way to go. So given that the epoxide ring opening is SN2, predict the following reactions. Okay, so if it is an SN2 reaction, you're trying to figure out which one of these sides to attack, you want to go to the least substituted side. So this is going to attack here. You form a bond to the nucleophile. That will get protonated. We get the alcohol plus nucleophilic addition. This one again, we're going to attack here on the back side. This bond breaks. We get a proton transfer. And that gets protonated as well. So these are all nucleophilic additions to the epoxides. You can think of these as under basic conditions because we have a bunch of minus charges. Ring opening under basic conditions will occur at the less substituted carbon. Under acidic conditions, we can also use those to open epoxides. Those are going to occur at the more substitute position. So we're going to start with a proton transfer. So we have X minus. In this case, the epoxide appears to be symmetrical, so we don't have to worry about which side it goes to. we get the addition of the X, and then we have our alcohol. If you have water plus the acid, so this is how we got the anti-diol in chapter 8. We had an alkene, which goes through the epoxide, and you add water to get that. If you add an alcohol, we will get an ether. So this is a situation where you have an asymmetric epoxide. This becomes protonated and is positive. So because this is happening under acidic conditions, when you go to try to figure out why it attacks here, you can think of if a carbocation, because it's under acidic conditions, were to form at either side, which one is more stable. So this bond starts to weaken. And that would form a carbocation at the tertiary carbon. So as that starts to weaken, this alcohol can attack there, and this bond breaks, or the bond fully breaks. When that happens, the methyl group gets pushed forward because we did a backside attack here. This becomes the ORH. Then we get a proton transfer. Just as we wrote on the last slide, under acidic conditions, the ring opening of epoxides occurs at the more substituted carbon.